Okay, so let's look at this problem that we have. We have a person that is walking along this plank. And question is, we're trying to figure out how far along this plank the person can walk before the beam starts to tilt. Let me read the question for you, just so you have some reference. Got a uniform beam, which means that the center of mass of the beam is going to be right here at the 2.5 meter mark, assuming that the beam is 5 centimeters in length. And continuing on, the mass of the beam is 120 kilograms. So we calculate the weight of the beam by taking 120 and multiplying it by G. So 120 is multiplied by 9.8. So we have 120 times 9.8. So that's how we come up with the 1,176 Newton. Might be a little fuzzy to you on the screen. Then we have a pillar here that's applying a pressure upwards. And as we read here, the length of the entire beam itself is 5 meters. It says on the left edge, one at the left edge and 3 meters from the left edge. So here's the one on the left edge, and then 3 meters from the left edge. We call it F of B. And we want to know how close to the right edge can this 68 kilogram person walk without causing it to tip over. So what we do here is we sum all the forces about some point, some reference point. We'll use that, even though F of A is going to go to 0. When this thing begins to tilt, there's no upward force on the object here, on the beam. And so we'll sum the torques. We know that if it's best case scenario, we're in equilibrium, we take the arm lever. So the arm lever is the distance to the force, or the line of action of the force. In this case, it's 2.5 meters. We multiply it by the force in question, which is 1176. We do the same thing for that upward beam, that pillar. That length is 3 meters. And likewise to the person. So the person is going to be called either X or 5 minus X. I use 5 minus X in this case. So it's going to be 5 minus X relative to that that person or that edge. And again, the beam is 5 meters long. And so we'll come up with this. This is if it's an equilibrium, best case scenario, but we're taking the fact that F of A is out, right? So maybe we could say almost in equilibrium. So just before it starts to tilt over, we assume that F of A is no longer there, and we'll solve the equation. So if you are looking at this in the summer of 2024, there's a typo. I went through it 3 or 4 times, and I realized that 1.6 as the answer, that given answer was incorrect. So my apologies. So you should have gotten 1.12 once you solve this. So you'll set up the equation. First equation gives you 2 unknowns, but you can solve for F of B. When you solve for F of B, when I kind of hold tight here, and then use your other equilibrium fact, you know that the sum of all forces in the y direction has to add up to 0 as well. But we're discounting F of A because F of A is no longer there. So if we track that and we keep that in mind, we can easily solve for F of B. So these are the only 3 forces an instant before this thing starts to tilt that are in play. F of B turned out to be 1842 newtons, And now we'll just go back and we'll sub back into this equation here. We extract out what X is equal to, and X turns out to be equal to 1.12. So you're gonna make a correction. And this is number 11. Those of you that are looking at this in summer of 2024. So make that correction. All right. Cheers. Take care.